Hi everyone, and welcome to the third week of Introduction to Causal Inference. In this lecture, we'll be introducing you to graphical models and how association and causation flow in them. And as a reminder, if you have any questions about the lecture as you're watching through, go ahead and just leave them down in the comment section and I'll make sure to get to them right away. There are 4 parts to this lecture. In the first part, I'll just be going through some basic graph terminology that we'll need for the rest of the lecture. Then I'll introduce you to Bayesian networks and causal graphs that will be essential throughout this course. And all graphs are built up of a few basic building blocks, so we can take these building blocks and analyze how association and causation flow in them, and that's what we'll do in the third part. Then in the last part, we'll take those building blocks, put them all together, and that will give us the flow of association and causation in graphs. Okay, so let's get started with some graph terminology. First of all, let's cover what I don't mean when I say graph here. So you might be thinking of when you plot a function, f of x, versus the inputs of that function x, or you could be thinking of a bar chart, for example. And both of these are not what I mean by graph here. So to tell you what I do mean by a graph, I'm going to have to break out the terminology machine gun where I just fire a lot of terms at you all at once. And this is pretty much the only way to do it. I just have to give you all this terminology right away so that we can cover the relevant concepts right afterwards. So please just bear with me while I do that. This is a graph. And these are the nodes in the graph. The circles are the nodes or vertices. The edges are the connections between them. And this specific kind of a graph is called an undirected graph. That's in contrast to a directed graph where these edges actually have direction to them. They're arrows. And directed graphs will be what we're working with in this course. A lot of ancestry-themed terminology is used in graphs. So for example, in this directed graph, A is the parent of its child B. So a parent is any node that has an edge going out of it, and then the child is the corresponding node that has that edge going into it. Then we say that 2 nodes are adjacent if they are connected by an edge. So A and B are adjacent here. And they're not adjacent if they're not connected by an edge. So A and D are not adjacent in this graph. We say that there is a path between 2 nodes in a graph if there's a sequence of edges that connect those nodes. So A to C to D is one path, but it can also be A to C to B. Paths don't need to go in the direction of the edges. Both of those are examples of paths, but then there are directed paths, which do need to go in the direction of the edges. So A to C to B is not a directed path, whereas A to C to D is a directed path because it follows only directed edges. And more ancestor terminology. So if A is the ancestor that we're interested in, all of its descendants are nodes that can be reached from A in directed paths. So B can be reached from A if you just follow the A to B edge. Similarly with D, if you follow the A to C and then C to D edge. So all of those are descendants of A. If we add this directed edge D to B, then we have a cycle. In this course, we'll almost exclusively be looking at graphs without cycles. So those are called directed acyclic graphs, or DAG for short. In this graph, A and B are parents of their shared child C, and A and B are connected parents here. But if we were to remove this connection between A and B, then we would end up with what's known as an immorality. So you have immorality when you have 2 parents that have a child together, but these parents are not connected. And in case you're wondering, that is real terminology in graphs. That's not something that I made up. Alright, so with that lesson in morality, I think we can conclude the graphical terminology portion of this lecture and move on to the Bayesian networks and causal graphs portion of the lecture. So let's start with no causality at all, just statistical modeling. We'll see that this is a theme throughout the course, statistical models versus causal models. But for now, we're just going to start with statistical modeling. So that means that we're modeling the joint distribution over n variables here, x1 through xn. And just from the chain rule of probability that always applies, we get this decomposition here. If we write that out for n equals 4, then we get this specific factorization. P of x1 times P of x2 given x1 times P of x3 given x2 and x1 times P of x4 given everything before it. So if we want to model this distribution, we need to model at least one of the factors, so at least the P of x4 given everything before it factor. And if all of these variables are binary, say, this isn't important for the argument, but let's just take them to be binary, then we can write a model for P of x4 given x3, x2, and x1 using this table. Okay, so to model this factor, we have to learn each of these parameters, these alpha 1 through alpha 8. And that's because there's 3 different variables that we're conditioning on, each of which can take on 2 possible values. So we end up with 2 to the 3 parameters. For general n, we end up with 2 to the n minus 1 parameters for the largest factor, for the factor that we're conditioning on everything before it. Okay, so just in statistical modeling, we already have a problem, and that's that we have an exponential number of parameters if we want to model these distributions with these tables right here. And this is because we're modeling the dependence of x4 on every other variable in the distribution. This is where Bayesian networks come into play. If I were to draw a graph for which variables each variable depends on, then I could get something more local like this. So here, x4 only depends on x3. So maybe we don't need to model the dependence of x4 on all of the variables, but just on x3. So we'll see how this helps us out shortly, but first let's discuss the local Markov assumption, which is given its parents in the directed acyclic graph, a node is independent of all of its non-descendants. So in this example that we just saw, here's a graph for it, and here's the factorization that we were to get from the chain rule of probability. In this example, we can actually simplify this last factor because x4, given its parent x3, is independent of every other variable in the graph, all of its non-descendants, and x4 doesn't have any descendants. So because it's independent of every other variable in the graph, we can simplify this last factor to just P of x4 given x3. Say we were to further remove edges from this graph, so if we were to remove the edge from x1 to x2 and the edge from x2 to x3, then my question for you is, how will the factorization further change now that I've removed these edges? I'll give you just a couple seconds to answer, so feel free to pause the video if you'd like. The answer is that now that x2 doesn't have x1 as a parent, it will no longer condition on x1. So that factor P of x2 given x1 will just become P of x2. And similarly, x2 is no longer a parent of x3, so the factor for x3 will no longer have x2 behind the conditioning bar. So here is the simplification. And we give this example to build up your intuition for a more general concept known as the Bayesian network factorization, which is the following. The joint distribution factorizes as the product of factors where there's one factor for each variable, and each factor is just the probability of that variable conditioned on its parents in the graph. And here you might notice that I'm using the word variable in a distribution kind of interchangeably with nodes in the graph. And that's something that you'll commonly see from both me in this course and outside of this course. It's normal to just talk about the variables in the distribution with the same labels as the nodes in the graph. Just talk about those interchangeably. If you remember from a couple slides ago, the way we actually did the example in the last slide is using the local Markov assumption. And then that example, we generalized it in this slide to the Bayesian network factorization. So we were giving the intuition for this implication that the local Markov assumption implies the Bayesian network factorization. And it turns out that the Bayesian network factorization also implies the local Markov assumption. So these two related properties are actually equivalent. And you can see proofs for this kind of stuff, for example, in Chapter 3 of Kohler and Friedman, which is a probabilistic graphical modeling book. Another important assumption that we will be using when we write graphs in this course is the minimality assumption. The minimality assumption has two parts. So the first part is just the local Markov assumption. To see why we're not satisfied with just the local Markov assumption, consider this graph, x to y. And this graph permits different kinds of distributions. So one kind of distribution is this factorization here. The joint equals p of x times p of y given x. And the local Markov assumption for this graph also permits the fully factorized distribution, so that's where p of x comma y equals p of x times p of y. In distributions that factorize that way, x and y are completely independent, right? So even though there's an arrow from x to y, x and y don't depend on each other. And that's not really what we want. It doesn't seem very intuitive. So the minimality assumption also adds this second part, which is that adjacent nodes in the DAG are dependent. And now that we've added this second part to the local Markov assumption, this graph, x with an edge to y, no longer permits distributions that factorize as p of x times p of y. It no longer permits distributions where x and y are independent. Rather, now that we're using the minimality assumption when we're talking about graphs, if we wanted to talk about that distribution where it's fully factorized, we would need to use this graph, x, y, without any edges in the graph. So if we were just using the local Markov assumption, then we could represent this fully factorized distribution using either the graph where it's x and y and there's no edge, or using the graph where it's x and y and they're connected with an edge. Both of those would be graphs that this distribution is Markov with respect to. This distribution satisfies the local Markov assumption with respect to both of those graphs. You can think of the minimality assumption as just giving us a way to select which of those graphs we're going to use to represent this fully factorized distribution. It means that we're going to use the graph that has the minimal number of edges that this distribution is Markov with respect to. Okay, so you can think of this minimality assumption as kind of like expressing our preferences for what kinds of graphs we'll use to describe different distributions. So the two assumptions we've seen so far are the Markov assumption and the minimality assumption. And the Markov assumption gets us to statistical independencies. It lets us read off statistical independencies about a distribution given a corresponding directed acyclic graph. Then the minimality assumption, when we add in that second part, we get statistical dependencies. So we can read off statistical dependencies in the graph, at least between adjacent nodes. So statistical dependencies can get a bit more complex when there's multiple paths between nodes. But we won't get into that until much later in the course when we see causal discovery. Okay, so now I have two questions for you to recall the answers to. The first is, how is the local Markov assumption related to the Bayesian network factorization? And the second is, what are the two parts of the minimality assumption, and what do we gain with the second part? Feel free to pause the video if you want to take a bit of time now to recall the answers to these questions. All right, so everything we just saw was purely statistical. There was nothing causal in what we were just discussing. And now we'll start to get into causal stuff. So first, we have to say, what is a cause? A variable x is said to be a cause of a variable y if y can change in response to changes in x. You may have also heard the terminology that x is a cause of y if y listens to x. This is terminology that Yuda Pearl uses. And I mean the exact same thing here, so if that makes more sense to you, go ahead and just substitute that in for yourself. Then, given a graph, we will introduce what we'll call the causal edges assumption. So in a directed graph, this means that every parent is a direct cause of all of its children. We introduced what a cause is in the previous slide so that this assumption is defined, and with that assumption, we get a bit more information out of our graphs. So we already saw the Markov assumption and minimality assumption and how those get us to statistical dependencies in our graph. And then when we add the causal edges assumption on top of that, we can talk about causal dependencies in our graphs. Right, so this will be key for talking about the flow of not only association, which is a statistical dependence, but also causation, so that's causal dependence. So for that, we need a DAG plus two assumptions, the Markov assumption and the causal edges assumption. And the reason I don't talk about minimality here is because the first part of minimality is the Markov assumption, and the second part of minimality is subsumed by the causal edges assumption. That's because if we have that, if a parent is a direct cause of its child, we have that causal dependence is flowing between those two. So statistical dependence must also be. That's the sense in which the second part of the minimality assumption is subsumed by the causal edges assumption. Okay, so we just went through a few assumptions. There's going to be a decent focus on assumptions in this course so that we know exactly what we need to assume to get to the causal statements that we want to be getting to. And importantly, we'll see that the DAG is how we're going to express a lot of our causal assumptions. Given that we are endowing the DAG with causal meaning using these other two assumptions here, importantly, the causal edges assumption. With that, we can conclude the Bayesian Networks and Causal Graphs portion of the lecture and move on to the basic building blocks of graphs. So this whole section will be about how association flows in graphs, and it will apply not just to causal graphical models, but also regular probabilistic graphical models, so models that are just statistical. Causal graphical models inherits a lot of the work that was done in these regular probabilistic graphical models. All right, so a general directed graph can be composed of a few different building blocks. The first is just two nodes that are not connected. The second is just drawing an edge between two nodes. So you can think of these two-node graphs as like the base cases. And then if you were to take the graph on the right, the one with the edge between them, and try to add more edges and more variables to that graph, there's three ways that you could do it. Three ways that you can add another variable with an edge to it. If you're adding another variable without an edge, then it's simple. It's just the graph on the left here. Okay, so the first one is a chain graph, which is just x1 has an arrow to x2, has an arrow to x3. The second one is what's known as a fork, where x2 is the parent of both x1 and x3. And then the third is the immorality, where x1 and x3 are parents of x2, but x1 and x3 are not connected. Okay, so with these three different building blocks, we can talk about general paths in graphs and whether association or information flows along those paths or doesn't flow along those paths. But before we get to that, I have another question for you, and it's what assumption tells us that x1 and x2 are associated in the following graph? So we'll first talk about dependence in chains and forks. Here we have a chain, and we know that x1 and x2 are dependent simply because of minimality or the causal edges assumption. Same with x2 and x3. But what about x1 and x3? x1 and x3 are also dependent, usually, and we'll depict this with this sort of flow of association or flow of information. And it flows from x1 through x2 to x3, or the other way around from x3 through x2 to x1. It's symmetric. And a reminder that when I say association, I just mean statistical dependence. Similarly, in forks, x1 and x2 are dependent from minimality or the causal edges assumption, and then the same with x2 and x3. And what about x1 and x3? It turns out that they are also associated. And it's because of this common cause x2 that they share. I'll be using causal terminology here, but everything that I say about association or statistical dependence applies just by the Markov assumption. I don't need the causal edges assumption. It just makes the explanations more intuitive. So x1 and x3 are dependent here because they share this common cause. Whenever this common cause x2 changes, then it's going to cause x1 to change and x3 to change in a corresponding way. So in both chains and forks, x1 and x3 are dependent. Another way of talking about that is that association flows along these paths between x1 and x3, or x3 and x1. And we'll now talk about independence in chains and forks. So it turns out that if we were to condition on x2, then x1 and x3 become independent, conditional on x2. We depict this conditioning with a light gray shading of the variable x2 here in the chain graph. So you can think of conditioning on x2 in this chain as blocking this path from x1 to x3. And similarly, it's the same in forks. When you condition on x2, it blocks the path from x1 to x3. It makes x1 and x3 conditionally independent. Okay, so the term that I've been using here is blocked path, and that's a very important term that we'll be using throughout this course. Similarly, when a path is not blocked, so when we don't condition on x2 in these graphs, then we have an unblocked path. This is when association is free to flow between x1 and x3. So in a blocked path, association is not free to flow, it is blocked. Alright, so that's all some nice visual intuition, but what about a proof? So the claim that we just made, which we're visually depicting here, is that x1 and x3 are independent conditioned on x2, which you can write this way in terms of this factorization. And that's what our goal will be in this proof, is to show this. So to do this proof, we start with the Bayesian network factorization. In order to write that down, we look at the graph, we see p of x1, and then p of x2 given its parent x1, and then p of x3 given its parent x2. That's what we've written down here in the Bayesian network factorization. Then we need to condition this whole thing on x2. So we can use Bayes' rule here, which just tells us to divide this by p of x2. And then if we notice that we already have one of the terms that we want to end up with, p of x3 given x2, then we know that we just need to turn this stuff in the red box down here in step 2 into the stuff in the red box up in our goal. That's how we can complete the proof. So if we just notice that in the numerator, we can combine those into a joint p of x1, x2, and then just apply Bayes' rule again. So we can turn this fraction into exactly what we want, p of x1 given x2. All right, so we just proved that x2 blocks the path from x1 to x3 in chains. Right, we proved that x1 and x3 are conditionally independent given x2. And you can imagine doing the same thing for forks instead of chain graphs. And feel free to do that yourself if you like. It's a similar process. Go ahead and pause the video now if you want to go through that proof. All right, we'll now move on to immoralities and how association flows in immoralities. So the question here is, are x1 and x3 associated? It turns out that unlike forks and chains, they aren't. So the association is actually blocked at x2 here. Because x2 blocks association, even when we're not conditioning on it, it has a very special name. So you might remember that x1 and x3 are called the parents of their child, x2. And that this is called an immorality because these parents are not connected, right? They're not married, but they share a child. So that might lead you to the term for this very special variable that x2 is here, collider. So colliders get their own special name because they block association here. It's different from what was happening in forks and chains where x2 in those graphs was just allowing association to flow through it. And the intuition for why x1 and x3 are independent is that they are just two events that happen to cause some downstream event x2. Right, so why would x1 and x3 be dependent? And just as we did a proof for conditional independence in the chains and forks, we can do a proof for unconditional independence here with immoralities. So we start by just marginalizing out x2. And next, we're just going to use the Bayesian network factorization. So the root nodes in the graph, that's the nodes that don't have any parents, x1 and x3, show up in their own factors without anything conditioning them. And then we have a p of x2 given x1, x3 because x1 and x3 are x2's parents. Then we can push this summation over x2 all the way inside, using the fact that the factor for x2 is the only thing that depends on what we're summing over, x2, along with the distributive law. And then this just sums to 1. We're summing over x2 for some conditional distribution over x2, and that sums to 1, so we get what we wanted. We get that p of x1, x3 factorizes as p of x1 times p of x3. In other words, x1 and x3 are independent. And what happens if we condition on a collider? Well, something very interesting happens. So if we condition on x2, it actually unblocks the path. right? So it's the opposite of what was happening with chains and forks. So even though x1 and x3 were independent unconditionally, then when we learn some information about the outcome of x2, when we condition on x2, that induces dependence between x1 and x3. To give you some intuition for this, we'll use an example of the perception that good-looking men are jerks. So say that good-looking is x1 and kindness is x3, so you get 1 for x1 if you're good-looking, 0 otherwise, and you get 1 for x3 if you're kind, and 0 if you're a jerk. And importantly, x1 and x3 are independent in the general population when you're not conditioning on anything. And x2 will be whether or not you're in a relationship. So x2 is 1 if you're in a relationship and 0 if you're not in a relationship. And the specific function for x2 is an and. Okay, so we'll say that you're in a relationship if you're good looking and you're kind. So when you condition on men who are not in a relationship, if this is the generative process of the data, that means that all men who are both good looking and kind are in a relationship. So you are not looking at those men when you're conditioning on not in a relationship. And you're looking at the remaining men. So the remaining men, because we used an and function for x2 here, the remaining men are either not good looking and kind, or they are good looking and jerks, or they are not good looking and they're jerks. But importantly, all of the men who are not in a relationship and are good looking are jerks in this example. So because we condition on not in a relationship, we actually do see an association between x1 and x3. In the general population, when we don't condition on x2 at all, then we don't see an association. And I'll give you a graphical picture of that now. Okay, say that looks and kindness are now real values on a scale of 0 to 10 rather than binary values. And say that each point is a person in the general population. So you don't actually see any correlation or any association here. Looks and kindness look pretty independent. But what if I were to group the population into the people who are in relationships and people who are not in relationships? And then if we were to take this data and condition on only people who are available, people who are not in relationships, we end up with this. These are the available men. So in this subpopulation, there is a clear negative correlation between kindness and looks. And that's because we have selected only the men in the population who are available. All the ones that are not available, they were what were in the top right-hand corner there. That's why this induced association, when we select a certain subset of the population, is sometimes called selection bias. All right, so we just saw that when you condition on a collider, it induces association between its parents. What would happen if you were to condition on a descendant of a collider? So here x2 is a collider and x4 is a descendant. Well, it turns out that that would also induce association between x1 and x3 if you conditioned on x4. The quick intuition for this is just that conditioning on x4 probably gives you information about x2, so it's a bit like a proxy for conditioning on x2, and we know that when we condition on x2, then that induces association between x1 and x3. That brings us to our next question, which is, in the three different kinds of three-node graphs, chains, forks, and immoralities, what can block a path? And that concludes the basic building blocks of graphs. So we saw forks, chains, and immoralities. Those are the main building blocks to build more general graphs. So given those building blocks and how association flows in them, we can now move on to the flow of association and causation in more general graphs. First, we'll give a more formal definition of what a blocked path is that we've been talking about. A path between two nodes x and y is said to be blocked by a potentially empty conditioning set, z, if either of the following is true. If along the path there is a chain or a fork with w in the middle of that chain or fork, and w is in the conditioning set z, then that blocks that path. Right, so this is what we saw in the chains and forks part of the lecture. And the other way that you can block a path is if there is a collider, w, on that path that is not conditioned on. So w is not in the conditioning set z. And none of its descendants are conditioned on, right? Because we saw that if you condition on its descendants, it's a bit like conditioning on the collider in the sense that it induces association between the parents. Okay, so that's what a blocked path is. And you can see how it uses the building blocks of what we saw in chains, forks, and immoralities. And then an unblocked path is just a path that is not blocked. So if you don't have either one or two here, then you have a path that is unblocked. And we needed this definition of blocked paths and unblocked paths to define a very important concept, which is known as deseparation. With the notion of a blocked path defined, it's really easy to define deseparation, and it's that two sets of nodes, x and y, are deseparated by a set of nodes z if all of the paths between any node in x and any node in y are blocked by z. And deseparation is such an important property because it implies independence. So, given that P satisfies the local Markov assumption with respect to some graph G, then deseparation in the graph implies independence in distribution. So here, this independent sign with P here means independent in distribution, and then this independent sign with a G here means deseparation in the graph. Okay, so deseparation allows us to read off conditional independencies in the distribution. And this is such an important theorem that we'll call it the global Markov assumption. It turns out that just as the local Markov assumption was equivalent to the Bayesian network factorization, the global Markov assumption is equivalent to the local Markov assumption. As I mentioned before, for the Bayesian network factorization equivalence proof, here too you can see the Kohler and Friedman book for proof of this. And because these two are equivalent, we'll often just refer to them as the Markov assumption, rather than specifically the local Markov or global Markov. And this very nicely matches the terminology that we use, where we say P is Markov with respect to G. It's just like saying P satisfies the Markov assumption with respect to G. Okay, so because deseparation and the associated blocked and unblocked paths concepts are such important concepts in this course, we'll now do a good amount of practice with them. So I'll be asking many questions, and at the end of each question, go ahead and pause the video if you want to try to answer the question. In this slide, we'll always be talking about whether t and y are deseparated given different conditioning sets, and we'll always denote the conditioning sets with shading in the variables. So the first question is, are t and y deseparated by the empty set? The answer is no. For example, there is an unblocked path from t to y going through m1 and m2. What about if we were to condition on m1? Then are t and y deseparated? The answer is still no, because there's an unblocked path going from t to w1 to w2 to w3 to y. Okay, what if we were to condition on w2? Then are t and y deseparated? Yeah, it turns out they are this time. How about instead of conditioning on w2, we condition on w3? Yeah, conditioning on w3 is still enough to block the path through the w variables. What about if we were to also condition on w2 in addition to m1 and w3? It turns out that that doesn't change anything, and t and y are still deseparated given those variables. Okay, what if we were to condition on x2? It turns out that conditioning on x2 unblocks the path that used to be going through the collider x2, so the path from t to x1 to x2 to x3 to y. So when we condition on x2 here, because we unblock that path, t and y are actually not deseparated, given this conditioning set. What about if we were to additionally condition on x1? Yeah, conditioning on x1 fixes the problem that we introduced when we were conditioning on the collider x2. So now if we condition on all of these gray variables here, we do have that t and y are deseparated by them. Okay, 2 more questions, and we'll use a new graph for these questions. In this graph on the left here, are t and y deseparated by w and x2? It turns out that even though w blocks the path from t to w to y, x2, because it's a descendant of the collider x1, unblocks the path down below. So t and y are not deseparated given w and x2 because of x2 here. What if we were to not condition on x2? Then t and y are deseparated because x1 is a collider, so it blocks the path from t to x1 to y. Alright, so let's get towards wrapping things up and talk about the flow of association and causation in this basic graph. Given the Markov and minimality assumption, we can talk about association flowing in this graph. So association flows directly from t to y, and from y to t, it's symmetric, and it flows from t to x to y, and from y to x to t as well. Then, when we add in the causal edges assumption, we can also talk about the flow of causation. So, causation, also known as causal association, flows along directed paths. The edge from t to y is how causation is flowing from t to y in this graph. And this is not symmetric at all. Causation only flows from t to y. It doesn't flow from y to t. This is because t is a cause of y, but y isn't a cause of t by the causal edges assumption. And one way we can refer to this association flowing through the confounder x here is just as confounding association. Importantly, it's not causal association. So if we look at the big graph that we saw 2 slides ago and we condition on the collider x2 here, we can see that association flows along all of these paths. And only the middle path through the m's here is how causal association or causation flows. The rest of these other paths are non-causal association. And this flow of non-causal association from T to Y is why association is not causation. That concludes this week's lecture. Go ahead and leave any questions or comments you have in the YouTube comments down below. And if you want to know right away when a new video or lecture gets uploaded, then go ahead and subscribe and hit the bell below. See you in next week's lecture.